Let's take a look at how we write a solution from a matrix that's in reduced row echelon form. So we can always identify that a matrix is in reduced row echelon form by looking at its leading terms. So in each row, if we circle the first non-zero entry, what we're going to see is that these entries are all equal to 1, assuming that there's some non-zero entry, that these entries move down and to the right. And if we look in any column containing one of these leading terms, we're going to see that the other entries in that column are equal to 0. So for example, here in this third matrix, if we look above and below these first non-zero terms in a row, we see that we have zeros. Okay. So all of these are examples of matrices that are in reduced row echelon form. Okay, so how do we write their solution if we know that we have a matrix in this form? Well, what we're going to do is we know how many variables that we have based off of the number of columns. Each column corresponds to an unknown. So in this first example, we've got 2 columns to the left of the augment. So we have 2 unknowns, and we can write out an equation for each of these, each row of our matrix. We see 1x plus 0y equals 2, or x equals 2. We see 0x plus 1y equals 3, or y equals 3. And our final equation tells us 0x plus 0y equals 0. Okay, this anything times 0 gives us 0, so we have 0x is 0, and 0 times y is also 0. So this just corresponds to saying that 0 equals 0. So it's not giving us any restrictions. This is always true, right? 0 equals 0 is a true statement, though not very interesting. Okay. And we can see here that we have just a single solution. That is, we need to see that x is equal to 2 and y equals 3. If we wanted to write this in vector form, we would write x equals 2, y equals 3. So this is a unique solution. Okay. All right, let's take a look at the next example. Here we have, again, we have a row of all zeros. We see that we've got 2 columns, so we've got 2 unknowns, x and y, that are to the left of the augment. And what do we read off? We have that 1 times x plus 0 times y is 2. So I'll write that out. And our second equation tells us that 0 times x plus 0 times y is 0. Okay. If we write out 0 times a variable, just as we just leave it off, we're going to write it just as 0. What do we find? This is x equals 2, and then this always true statement that 0 is equal to 0. What can y be? Well, there's no restrictions on what y can be. All we need to satisfy is that x is 2. Okay. And so if we look at our, if we write our solution out in this vector form, well, we would say, well, x has to be equal to 2, but y can be anything. Okay. And so in this case, we have what's called the infinite case. We have infinitely many solutions. for any value of y will satisfy, as long as x is equal to 2, will satisfy this first equation that x equals 2. And it's always true that 0 is equal to 0. Okay, let's look at our next example. Take a moment. I'd like you to think about how many unknowns we have in this case. Okay, so here we actually have 5 unknowns. So that's one column, one unknown per column left of the augment. So I'm going to number these instead of using letters. I'm going to call them x1, x2, x3, x4, and x5. Okay. We have just 2 equations in these 5 unknowns. So what do we see? We have that x2 plus 2x3 plus 3x5 equals 2. And we also see that x4 minus 5x5 equals 1. Okay. And because we know that these leading terms only show up in just one equation, we're going to find it convenient to solve for it. We can write x2 as negative 2x3 minus 3x5 plus 2. And we can write x4 as a function just of x5. So it's x4 is 5x5 plus 1. Okay. And notice that these are the only 2 restrictions. So we can say, well, x1 can be anything. It doesn't appear in these equations at all. x2 is governed by this equation. x3 can be anything. x4 is given by an equation. And x5 can be anything. So we'll call x1, x3, and x5 free. And if we want to write down our solutions, we can use a 5 tuple. And our free variables, we're just going to write as themselves. So x1 is just itself, it's x1. It can be any value. x2 is given by this equation, negative 2x3 minus 3x5 plus 2. x3 is itself. x4 is given by 5x5 plus 1. And x5 is also free, so we're just going to write it as this. And so what we've done here is we've written the leading terms as functions of the other unknowns. Okay. In the next section, we'll give these slightly different names. The variables corresponding to leading terms are called pivot variables, and the ones, the others are called free variables. Okay. So our free variables, which are the ones that weren't leading terms in the reduced row echelon form, just appear as themselves because they can be any value. Okay, one last example to make sure we've got the hang of this. Here we have an augmented matrix. Take a moment to look it over. How many unknowns do we have? Okay, we've got 3. I'm going to call them X, Y, and Z. Okay, and if we want to write this out, what do we find? We have x plus 2z is equal to 0. We have y minus z is 0. And we have 0 times x plus 0 times y plus 0 times z is equal to 1. This last equation, let me write it out a little bit more fully. 0 times x is 0, 0 times y is 0, 0 times z is 0. So what this boils down to is just the statement that 0 equals 1. Well, that's not true. Okay, so in the case that we see zeros to the left of the augment and we see something non-zero on the right side, this will mean that solutions will satisfy that 0 is equal to something non-zero. And so this corresponds to having no solutions. Okay, because it's impossible to choose x, y, and z to make 0 equal to 1. All right,